Good morning, everybody. Welcome back to Non-Euclidean Geometry. Play for today is I have the long-awaited Quiz 2, and then we are going to spend the rest of class continuing our discussion from last time of instance geometry. Looking mainly today at how can we prove some propositions that use instance geometry, meaning from only the axioms of instance geometry and not from our intuition. How can we still prove results? As far as office hours go, this is what I plan to put Friday. I've got office hours today and Wednesday after class and from 2 to 3, and tomorrow at 11, and from 1 to 2. And as far as homework 2 is due on Wednesday. A few questions in there about mathematical logic stuff that we did last week. I apologize for missing class on Friday. I've been having some cold symptoms, woke up Friday morning with a nasty headache, and decided, no, I cannot teach like this. I'm sure you all can feel it. So, apologize for having to miss class. If I miss any more classes due to sickness or for whatever reason, I'll do some way of trying to make it up. I planned on missing one class. Not anymore, and might make some recordings or do some extra session outside of class or something. We will see. Yeah, homeworks. Finally, homework 1 is getting passed back. You've been sitting on my desk ready to pass back since Thursday. Let's see. Chicken. General comments on the homework. Overall, if you're confused about why I took points off or something, or why something wasn't quite accurate or complete, I encourage you to come by and talk with me. I'm waiting on one more student to turn in homework for very late reasons, but once they do, I will post solutions to the homework on Canvas. You can go and take a look at my solutions, kind of what I was looking for and what you can expect. But with that in mind, any questions or comments before I pass out today's quiz? Now, I believe, Elaine, your class said that you wanted to joke after the quiz, so don't joke right now. All right, with that, go ahead and put everything away. And take about 10 minutes, and it is quiz time. I'm going to write some stuff on the board, but that's just instance action stuff that you don't need for the quiz, so ignore my writing.
I drop a rock on her from, I would be in the air, and it lands on the ground. Quite sick, right? It hits the ground. Quite the moment before it hits the ground, and then
go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Alrighty. What do mermaid mathematicians wear? They wear algae bras. Okay, so if you recall last Wednesday, we had started talking about the idea of instant geometry, where we're building up from scratch a system of axioms, kind of following along in what David Hilbert did at the beginning of the 1900s, and trying to come up with a system of axioms for geometry that kind of ultimately avoids a lot of Euclid's flaws and imprecise language as much as possible. And so if you recall, we have these three terms, points, lines, and incidents, which we very specifically did not give definitions for yet. Right now, we're not defining these terms, they're just out there. And we have these three axioms that we assume about how these three terms relate to each other. We said for every point P and Q not equal to P, there exists a unique line instant with P and Q. So that was our instance axiom 1, which is the same as the modern version of Euclid's first postulate. And if I have a P here and a Q here, there exists a unique line that goes between them. Our second instance axiom says that if for every line L, there exists at least 2 points instant with L. So in other words, you give me a line, I can find 2 points on that line. I maybe can find more points, maybe there's only 2 points, but I can guarantee you that no matter what line you choose, I can find at least 2 points on that line. And finally, instance axiom 3 says there exists somewhere out in the universe 3 distinct non-collinear points, meaning 3 points, let's say P, Q, and R, where no line goes through all 3 of these points. This does not mean that any set of 3 points can't be collinear. There certainly can be 3 points that do all have a line going through them, like these 3. But somewhere out there in the universe, there happens to be 3 points where no line goes through all 3 of those points. If we want, we can give these points a special name. P hat, Q hat, R hat. Give them hats because they're cold. They're out there in the universe somewhere. Maybe they don't have a furnace. So these are going to be the only 3 things that we assume about points, lines, and instants, whatever these terms may mean. And what I want to do today is to talk about how, just from these 3 axioms alone, and our definitions for terms like parallel, concurrent, collinear, how can we prove different propositions about what must be true given these 3 axioms. And the first one I want to look at today is going to be proposition 2.1, which is going to say that if L and M are distinct lines that are not parallel, and write it slightly differently because I'm lazy. If L and M are distinct non-parallel lines, then L and M have a unique point in common. And by in common, I mean incident to both lines. So this is something I claim isn't going to be an axiom. This is not going to be something that we just assume, but I claim this is something that we can prove from our instance axioms. That if the three instance axioms happen to be true, I claim this result must also be true. A note on the numbering. When I say proposition 2.1, that from here on out, whenever I give like a proposition number like 2.1, that means it's 2.1 in the book, the course textbook. So you can refer back to it more easily later on. So 2.1 means it's the first proposition in chapter 2. Let's see if we can prove this. So as part of our proof, all of our intuition flies out the window. We don't know anything about points and lines and what it means for a point to be instant to a line, other than what's guaranteed by these three axioms. So what is this saying? This is saying that if we have two lines out there, L and M, that are non-parallel, meaning they intersect somewhere, there has to be a unique point in common. What does unique mean in this context?
They don't intersect at multiple points.
Yeah. In fact, they intersect at exactly one point. They can't intersect at multiple points. So this proposition is actually a sneaky type of two proofs in one combined. In that, in order to prove this proposition, we have to prove two separate things. We have to, first of all, prove that L and M have at least one point in common. We have to show that there is a point in common to L and M. And then we have to prove uniqueness. In other words, we have to show that there can't be, once we show that that they have a point in common, we have to show that there can't be more than one point in common. So this is kind of what's called, colloquially, an existence and uniqueness proof, where we first show there exists a point, and then we show that it's unique. So let's start off with existence. I want to prove that if L and M are non-parallel lines, then there has to be at least one point that the two lines have in common. So we're going to, first of all, define our terms, define the things we're going to be working with. We're going to let L and M be distinct non-parallel lines. How can we show that these two lines have to have at least one point in common? Jack?
Does it come straight from the definition of parallel lines, which is two lines are parallel if they have a point instead of both of them? So if they're not parallel, then they... Or sorry.
As I said, I think you meant the other way around.
Other way around. Two lines are parallel if they don't have a point incident. They're non-parallel, therefore they have a point incident.
So you're saying this just follows immediately from the definition of what it means for two lines to be non-parallel.
Yes.
That sound reasonable? Luke?
I would just qualify that where it's that two distinct lines that are not parallel. Because if they were not distinct, that would still fulfill them not being parallel. You have to say that they're distinct as well.
True. I think technically we could say if they happen to be the same line, then they're going to have a point in common by instance axiom 2. But the fact that we have distinct non-parallel lines means by definition, since parallel means, as Jack put it, parallel lines are lines that don't have any points in common. If they're non-parallel, that means they have to have at least one point in common. So this one, we don't even need an axiom. We can just use the definition of parallel directly to say that there's at least one line. Then, by definition, I'll say, since L and M are not parallel, they must have at least one point, I'll call it P, in common. Okay, I like it. Short and sweet and to the point. Whenever you're proving an existence theorem, a result like this, you just have to give some reason as to why your thing has to exist. In this case, L and M are distinct non-parallel lines. Jack wanted to say, why do these points have to have, or lines have to have a point in common? He said, oh, well, we can just immediately use the definition of parallel to say why they have to have a point in common. And Luke made an excellent point too about we're using the fact that they're distinct non-parallel lines. Although if they're the same line, then of course they're going to have points in common too. The distinctness, I think, is going to be more important in the next part of our proof, which is the uniqueness part. Any questions or comments so far? So now I want to prove uniqueness. Which is to say, I want to show that now that we know these two lines have to have at least one point in common, we want to show that they can't have more than one point in common. So, someone who's taken a proof course before, I know there's a couple of you in here. How do we prove uniqueness of something as a general strategy? Elaine?
Assume there are two that fulfill the conditions and then prove that they're equal.
Yeah, that's a good strategy for showing something is unique. Assume that there's two of them, then show that those two have to, in fact, have been the same to start with. I'm going to write this as sort of an aside up here. This is not part of the proof. This is just kind of a strategy. So you'll maybe have this in your notes. Assume there are two, then show they must be equal. Because if you assume that there's two of something satisfying a property, and then the fact that there's two of the things satisfying the property means that they have to have been the same thing, that's enough to guarantee that there can only be one of the thing at most that satisfy that property. And then combine that with our existence, that's going to tell us that there's exactly one thing satisfying the property. In this case, that there's exactly one point that happened to lie on both L and M. That happens to lie on both L and M. So let's do that, Elaine. I like your approach here. So we're going to assume there exists two points, P and Q, in common with L and M. We're assuming there's 2 points, P not equal to Q, incident with both L and M. And I want to show something has to go horribly wrong here. Luke, any ideas what we could do?
Postulate 1, for every point P and Q is not equal to P, there exists a unique line L incident with P and Q. That would make both L and M the unique line.
Oh, is that something that can happen?
No, since they are distinct.
And here's where we're very much going to need to rely on the fact that L and M are distinct lines. But yeah, I think you're right. Luke's making an interesting observation that we have 2 points, P and Q, that are not the same point, and they're incident with two lines. Whereas incidence axiom 1 says if you have two distinct points, there has to only be a single line that's incident to both of them. Interesting. It sounds like you found a contradiction, so to speak. But, so let's say, but by incidence axiom 1, since P and Q are not equal, there can only be one line incident with both. So in other words, something has gone horribly wrong. So what does that tell us? It's going to tell us P must equal Q, because if we assume that they weren't equal, something terrible happened. And so L and M can only have one point in common. Any questions or comments? Steph?
Is this just for like straight plane geometry? Because if we think about something like spherical geometry, the first axiom doesn't really make as much sense.
Oh, no. I don't know. We have to define what points, lines, and incidents are. It could be in a straight plane, it could be in a plane, it could be anywhere, as long as these three axioms are satisfied. But I very specifically not are going to say, I don't know, is my answer to your question, because we haven't specified yet. Later on, when we give definitions, we're going to look at different scenarios. One where we are in kind of your standard planar geometry, and some others where we're not. Kind of answer where you're going with this. But what do? We proved a proposition has to be true, not relying anything on our intuition about points, lines, and planes. Intuition and pictures didn't play any sort of role here in our proof. Instead, we only used our definition of parallelness and one of the axioms, incidence axiom 1 specifically, and kind of our rules of logic. By the way, what type of proof did we use here as part of our uniqueness proof that we talked about last week? Kind of the proof showed up. Like?
Proof by contradiction.
Yeah, this is a proof by contradiction, a reductio ad absurdum proof, where we assume the opposite of what we wanted to show, that there's multiple points incident with L and M, and then showed very quickly that that leads to a contradiction with incidence axiom 1. Something happened that incidence axiom 1 guarantees cannot happen. So this was, in fact, another reductio ad absurdum proof sort of baked into the larger proof. And in general, that's a good way to show you, that's a standard way to prove uniqueness, is to assume there's two of thing, and then show those two things have to be equal. Any questions or comments? Okay, so we proved this one. It's your turn. I have a group activity now where I would like for you all to prove proposition 2.3, and if you have time, proposition 2.5, where proposition 2.3 says for every line L, there is at least one point not lying on L, and for every point P, there exists at least two distinct lines going through P. And my challenge to you is to see if you can prove these without relying on intuition at all, relying only on the incidence axioms and definitions for things like, well, actually, no, parallel, no, just relying on the instance axioms. So let's see. I'm going to have you all break up into groups of 3 to work on this. So let's see. group of three. Break up Steph and Becca here. Group of three. 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 So here's your challenge. I want you all to see if you can find a way to convince yourselves that you've proven proposition 2.3. See if you can construct a proof of this. And then, if you have time, take a look at proposition 2.5 as well. And then we'll come back together here in a few minutes and talk about what you all found.
So I'm just saying,
So this to say alpha one by axiom 2, there exists these 2 points sensitive on L. What does that mean? Like this. Yeah.
I feel like that's what the most obvious that that's all points by axiom 3 would be, I don't know, yeah,
Well, that's for one line L.
Yeah.
You can say. It's not more.
or every line L there's a but that, if there were,
There's at least 2.
I feel like we could do like a by condition, if there were any line that all points are lying on, that would
We also use axioms
every
too.
point by axiom 3 because
There's
they
one.
will.
That's what I want to say. There's a part of me that thinks, since
I
it's
will-
axiom 3, that there's like a point and all around line, does that mean that like there could be 3 other points in the system?
You could just start with.
Yeah, actually.
Draw a line.
so if you just,
You think what?
I think.
Oh,
that
right.
so say after that axiom line,
Yeah.
and then
There's a
assume that all points lie on L.
How do we prove that the point is not?
But then by definition collinear, that means that all points are collinear, right? If there's no point lying on L,
Yeah.
they're all collinear by definition.
Yeah.
But this question is by 3, since there must exist 3
So
distinct
there's
points. So then,
It would be.
thus our
So
assumption is
we should use
all points are collinear,
Start
at least
with
one point.
L
That
is
makes sense.
one,
Yeah.
that's just the line from the other one, and then we'll
We use axiom 3 to have 3
So
distinct
we have
non-collinear
that
points.
there's
Just
maybe
keep
one
putting them on
plus,
so
and
we
then
like
that
As
there's.
a contradiction.
They'll come.
There are 2 points on the line.
So should we consider the one?
Each one.
Yeah. Great. So we did.
Then every other point would also be inside that line. And that would violate axiom 3.
Oh, yeah.
Does that make sense?
Or could we say line
I mean, I feel like you gotta say.
Assume that there are lines.
I'm not sure if you use IA to prove it, but I know, like, that you don't need to, you know?
Yeah.
Because from that you can see that, you know, point R has to be.
So we're saying that the line is.
So
we're gonna say one point, not an
That's whereas IA is saying that they are inside,
Because.
so, you know, at least 2, that means it can be
For every point.
I mean, 2, 3, 5, 100, a billion, you don't know.
a zillion.
A billion is not equal.
Assuming it's
Two and a
zero.
half.
It's a unique line out.
Sure,
But the point is that has no word.
Yeah.
Wait, no, that's a definition for point.
I was gonna say, I don't know, you don't know that, you should anymore.
Then in
Um,
there exists
So linear would
3
give it-
distinct points.
I think fractional point, having, the existence of fractional points relies on having a definition for points. It's gonna be my answer to that. You don't have a definition.
Well, how do we know that those like the 3 distinct non-collinear points exist on like 2 on the line?
Oh, we didn't number.
So proposition 2.5, right?
Two.
There exist at least two distinct lines.
We don't put those two points on the line.
I know, but
That would be maybe like point P.
And then you have the two time thing, right?
It is not,
Three and one.
you can't make a line through all
Yeah.
three.
It's saying there's three.
One again, then you can make a line through
Use
P and
the
R.
second.
So,
Thanks. Okay, so one, I'll make a-
Probably just a good writing.
No, because there
what-
is-
What are you guys saying about?
Just for
Do a retread.
okay, so there exists.
Hey, that's perfectly fine. A lot of times I
Such
don't know how many proofs I've tried writing over the years that I just start over from scratch. So, because something didn't work. That's how you know you're learning something. One strategy didn't work, so you have less strategies to choose from.
I think they're all very viable.
And so we already have two of those points, so we should find one
Just the first one.
Like
the next week, just want the first one.
Think about the second one if you have time. If you feel pretty good on the first one, then, yeah, go ahead and start thinking about the next one. We're gonna talk about both.
Assuming that there's more than one point.
I feel like when we use incident axiom by, sorry, as a number three, right, that almost throws it. I agree, you can choose, yeah, like another point, it's not on the same line, right? Right, so, yeah, you'll have 3 points, like, I mean, if you plug it from the proposition, you just
That's
throw
kind of
it
what
to, you know what I mean?
So I made a line.
That is true too, yeah.
Yeah, and use axiom one to the next, like,
Oh, sorry,
here's
two lines
our
that
PR or something.
That line.
Yeah, instead
I
of
don't know, I think all of those
I just are.
I already forgot what
I
you
guess,
said.
well, I would
I
say,
think all of them.
Yeah, okay.
I would say probably like 2.3 and then incidence axiom 1.
Incident axiom one.
Go team.
Yeah.
Because there's one point that's not out of the L.
Yeah.
For every point.
Go ahead and think about,
So that
let's go ahead and take about 1 more minute and then we'll come back together as a class to talk about proposition 2.3.
So I just did 2.3, let you do 1, right, and then there exists. I'm still writing an R, so yeah, you can also just write one, right, also then by I, there exists.
Once you prove something, you're allowed to use this. So you can just
Yeah, yeah, that makes sense.
So then there's two distinct lines.
Except for one thing. It says there exists three distinct non-collinear points, but what if like PQRST are all linear, and then like Z is the one that makes one set of 3 non-collinear, the rest are linear?
There exists. Well, I'm
Does
just
that
saying,
fit?
well, then I would just use Z instead of Q, you know? Like I'm saying, there must exist Q and R that are both non-true.
Sounds like it's quieting down, so let's come back together and, let's come back together and talk about this. Yeah, here's some great, here's a lot of great thoughts to kind of walk around the room listening to you all talk about your ideas. So proposition 2.3, we're trying to prove that given any line L, there exists at least one point not lying on L that's not incident with L. I'm being a little bit sloppy here and saying things like lying on L. When I say that, think incident too. What do y'all think? Let's see. Katie, what were your group's thoughts on this one?
So first, I kind of assumed that there was a line L that all points are incident to.
Ooh, okay. You know, let L be the super line that contains every point. Okay.
So which is just, direct contradiction of the proposition, and then by definition, all points would then be collinear, but that violates incident axiom 3. There are 3 distinct points somewhere that are not collinear.
Okay. So basically, you said if the proposition, so you assumed that there's a line L where there does not exist at least one point, not lying on L, there's a lot of negatives. So meaning you assume there exists a line L incident with every point, and then said that, but that would have to contradict instance axiom 3, therefore by contradiction, whatever line L we start with cannot be incident with every single point.
Right.
Ooh, interesting. I like this. This is not what I had, but I like it. So, we'll write out Katie's proof. And then we'll write out another version of the proof and see if we can compare the two. So, Katie, how did you start your proof out?
So first assume that there exists a line L where there does not exist a point not lying on L.
Okay, so I'm gonna write it out slightly differently just to clean it up to match my style a little bit better. So we're gonna L be a line to start. We're gonna define the type of thing, the object we're working with. And you wanna assume L is incident with every point. Okay?
And then I don't know if this is necessary, but then it said by definition all points are then collinear.
Okay. Thus, all points are collinear.
But this contradicts incident axiom 3, which says that there exist 3 distinct non-collinear points.
Contradicting instance axiom 3, which guarantees the existence of 3 non-collinear points.
So it can't be true that there is any line L that is incident with all points. That is to say that for every line L, there is at least one point not lying on L.
Okay. Thus, L must have at least one point to which it is not instant.
Yes.
Okay. Did he assume the opposite of what you wanted to prove? That there's a line L that is incident with every single point. Found a way to show that that leads to a logical contradiction. Contradiction specifically of incidence axiom 3. And thus it can't have been the case that L is incident with every point, thus there has to exist at least one point to which L is not incident. Yeah, think about that. All right, everybody's going to be very quiet, so I'm going to start cold calling. Steph, what do you think?
Sounds good to me.
Sounds pretty solid? Jacob?
That's a bold assumption, the first line.
It's a bold assumption that L is incident with every single point. It's assumed, well, looks to me like she's assuming the opposite of what she wanted to prove. And then show that assuming the opposite leads to a contradiction. It is a very bold assumption. Assume L is incident with everything. But you were able to show that that assumption leads to a contradiction, so just because it seems very bold, translation counterintuitive, doesn't mean it's not something you can assume. Doesn't mean it's not something you can't assume as part of the proof. Classic double negatives. So this is I actually thought this is a nice and great way to prove this using reducto ad absurdum, a nice proof by contradiction. Follow-up question. Did any group prove this a different way? Brianna?
We used incidence axiom 3 and incidence axiom 1 to prove that there are 3 points first, and then we prove that there can be a line through two of them, but there can be a point that's not on that line, so we make that line L, and then prove that there's at least one point not on line L.
Okay, so you use instance axioms 3 and 1 to assume that there's 3 points. So you join the two of them by instance axiom 1 and then said, but it would violate instance axiom 3 for that third point to be on the line. Interesting. We don't have enough time for me to write that all down, but what do y'all think about Brianna's idea? Elaine, you're making faces.
Yeah, I don't know, because I don't know if that covers every point. You know, if you pick 3 arbitrary points, you didn't necessarily pick the 3 distinct non-collinear points.
So if we start with 3 arbitrary points, bad things happen. We don't know about arbitrary points, we just know that there are 3 points that are non-collinear. I think I would agree with that. I think Brianna, you can make a slight tweak to that. You could make your version of the proof actually work out nice. Where I don't think we need to use instance axiom 1 at all. I think you could just say, by instance axiom 3, there exists 3 distinct non-collinear points. If L is a line that happens to pass through any 2 of them, it can't pass through the third. Therefore, at least one of these 3 points, P hat, Q hat, and R hat, can't lie on your line L. Therefore, there exists at least 1 point not lying on L, no matter what line L you start with. You can show that one of these 3 points is not beyond. Simple, effective, more of a direct proof than Katie's proof, which in that it doesn't really rely so much on a proof by contradiction, but I think it works. Moral of the story. Sorry I didn't have time to write this down, but we're out of time for today. But moral of the story, there can be multiple logically valid ways to prove a proposition like this. There's not always going to be one way. Sometimes you can prove something directly that you could have also proved by contradiction. And so moral is, just because you had a proof of something that didn't match Katie's or Brianna's for that matter, doesn't mean that it's logically invalid. All right, we'll talk about 2.5 and on Wednesday, and also on Wednesday, we're going to come up with our first set of definitions for points, lines, and instants. And our definitions may surprise us. Have a good rest of your day.